All right, guys, we're going to cover two sections, 12.3 and 12.4. And first, we're going to start by going over the idea of an orbit. Yesterday, I gave you a interactive on some general features on orbit, but still didn't really explain what exactly an orbit is. So first, we're going to look back at the equation from section 12.1, known as the law of universal gravitation, which, if you recall, is that the force of gravity between any two objects, m1 and m2 in the universe, multiplied by the gravitational constant, which was 6.7 times 10 to the negative 11th, divided by r squared, r being distance between their centers. So I'm going to do something, a theoretical thought example that Newton gave at the time, applying this, assuming one of those masses in that formula was the Earth or another planet. All right, so we're going to all pretend in a perspective where we could look down at the Earth. Maybe we're up in space or something, and we could see the Earth as such in this view. And we're going to just pretend there's a theoretically crazy tall mountain that some object, this green dot is going to be that object, is going to be shot from. And it's going to be shot tangentially. So right now I'm going to shoot it whatever the velocity is set out, currently 3,500 meters per second, which sounds like a lot and is, but when we're on the perspective of looking at the Earth from afar, probably isn't really that fast. And I'm just going to hit play and fire the object. So, as we would probably expect, the object falls back to the ground. Now, that doesn't look like a very big distance here to us in this little simulation, but if this was like actually to scale, going that far around the globe is pretty darn far, right? So I'm reset it, and this time I'm going to crank up that velocity a little bit to about 500 meters per second to 4,000 meters per second. And it goes a little bit further, right? So let's crank it up again. We'll go 1,000 this time. I'll hit trace path now so you can see exact path. Oh, it's not tracing it. All right, so a little further, right? A little further. And why? Because the force of attraction between that object and the Earth, as described by the law of universal gravitation. Let's go up another 1,000 meters per second. And it goes a little further. Now you just start kind of catching on to the pattern here that if we keep cranking this up, that eventually we might just get enough velocity, and right there it was, just enough that it comes the whole way back around to the person who shot the object. So, and that really is describing to us what exactly an orbit is. When something is in orbit around something else, for example, the moon around us or man-made artificial satellites around the Earth, those are actually falling towards the Earth, this International Space Station, a space shuttle put in orbit. All those things are actually falling towards the Earth, but they never hit Earth because they're going at a speed that's tangentially fast enough that they're outrunning the curvature of the Earth, like this object. So things in orbit are falling, which leads us to a better explanation about the weightlessness topic. Remember, we had always said that there's no such thing as weightlessness. It's just a weightless-like feeling. It's because of astronauts maybe being in orbit in the space shuttle are in a constant state of falling when they're in orbit. And remember, if you're falling, nothing could push back on you. Like we always said way back when we did free fall, if you were falling and you had a scale underneath you, it would read 0 because there's nothing to push back on you to feel the sensation of your weight. So you sure as heck do have weight if you're an astronaut in a space shuttle, because you're falling towards Earth when you're in orbit. But there's nothing to push back on you, and you're constantly falling around the Earth. And a very small window of what velocity is needed to orbit a large object like a planet or star or moon in order to stay in orbit. And that is based on the gravitational force of attraction and the distance the two objects are apart. Now, remember, this is a theoretical example, and nothing could actually orbit this close to the Earth's surface because of the atmosphere. The atmosphere would produce too much friction, and whatever velocity we would set this thing to orbit at, it would slow down too much to that resistance of air and eventually back down to the ground. So that's why everything that orbits in space due to no resistances, atmospheric resistances. So we've already seen if you're not going fast enough, you'll crash into the thing you'll be orbiting. But what if we go too fast? So let's go well beyond whatever it was set. So crank it up some, hit play again, and it's gone. So if you shoot something too fast, you give it too much momentum, and it's able to completely break away from that force of attraction between the two objects, and bye-bye, you have an object flying off into space randomly, and you're never going to get that thing back then if you try to set it into orbit, which actually through error has happened to scientists and engineers before. To make a long story short, there was some confusion in the navigational system of a satellite once that NASA made. This is probably 20 to 30 years ago, probably close to 30. And just some unit errors and miscommunication, they sent a satellite up into orbit and shot it too fast, and it escaped, and there was no coming back because there was no system designed to bring it back, because that wasn't supposed to happen. Anyways, that's generally the idea of how to get something in the orbit. And hundreds of years ago, Newton and other physicists of his day figured out how to get things into orbit when the technology wasn't even close to present to do it. So once we had rocket propulsion in the early 1900s, and 1940s, it was kind of refined, and we had a good idea how to propel large objects with rockets. Then it wasn't much later until the first satellites were being shot into space in the going into the 60s and whatnot, using the equations that Newton predicted hundreds of years before them. So anyways, now to some formulas behind this stuff. So remembering this equation from section 1, remembering back to something we studied during the energy unit. This is actually a force as a function of separation distance r between the two objects, right? If you recall, we had some force, we called them force distance functions back in our first energy unit, whatever chapter that was. And we said if you had given the force as a function of distance, if you took the integral of that, that would give you the potential energy. So if we would take the integral of this function with respect to r, that's our new equation in the new section 12.4. So I'm going to flip ahead now in the notes. And the result of it was at a negative integral, if you remember, and that results in this formula. U is potential energy is equal to negative big G. We're going to make one of the masses the mass of the Earth. However, in this formula and any of the formulas in the next few sections, whatever the mass of the Earth is, also be substituted with the mass of anything else we're orbiting around. So if we're on a problem where we're not orbiting the Earth, or we have something in orbit around the sun, then you could change that 50 to S, or whatever planet we're dealing with. We're going to set it for Earth right now because most of our problems and examples will be with that. So mass of the Earth times any mass m, this would be the object that is orbiting the Earth or whatever planet or star we're talking about, and there's that distance r. But that formula from the negative derivative of the force universal gravitation function. And as we just showed in simulation, with what an orbit is, there's a velocity which, if you shot it too fast, it would escape this gravitational pull. And it's a little bit lengthy of a proof, but it's in example 12.5. You don't have to view it. The result is that this is the escape speed. If you would take the square root of 2 times g times the mass of the object in orbit divided by the distance r. And that would provide us with the exact number, and anything beyond that number, if you tried to shoot something that fast, that far away, it would be able to break that pull. By the way, don't forget this r represents the distance between the satellite to the center of the Earth, or the center of what we're orbiting around. So we had to do this in an early problem, and sometimes that number is given all complete. Like if we're given the distance the object goes away from the surface of the Earth, we would have to also add to it the actual radius of the Earth to get this r. We had another problem. I'm just reminding you of that. Okay, so with that, section 12.4 and 2 as well, because it all kind of binds together here. So more about the motions of satellites. Now, in the interactive I gave you guys, the main point of it was looking at a feature of an orbit called the eccentricity of it. So if you haven't completed that, you might want to do that. But most orbits of like planets around stars and such are elliptical, or at least a little bit of ellipse, some a lot. That's like an oval pattern. And there's this value called the eccentricity, you should have noticed in that interactive, that when it's further away from zero, it's more elliptical, like more stretched out oval. But when you have an eccentricity that's closer to zero, those orbits are very circular, nearly circular. So with that in mind, we're going to look at an equation that's specifically written for circular orbit, or something pretty darn close. And man-made satellites are all very, very, very close to a perfect circle orbit, or a very low in eccentricity, close to zero. And in that case, the speed necessary for that to orbit is given by this formula: the square root of big G multiplied by mass of the Earth divided by r. R being that same r value that I had re-explained above. So once you decide where you want to put a satellite, like the altitude of it, which is essentially how far away it is from the center of the Earth, then this simple formula would tell scientists and engineers the velocity they need to fire it at, just like firing things from that top of that Newtonian mountain, in order for it to stay in orbit. Not go too slow to crash down, not go too fast to fly out. Now, since we are talking circular, here comes some old formulas for circular motion. Again, so if it's a very elliptical orbit, these equations wouldn't exactly work. Some tweaking to do with them. But we're only going to worry about circular orbits. So if you recall, this formula is just a flipped around formula. Remember the V for something in circular motion, V equal to 2 pi r over big T, the time period, the time it took to make one revolution. Well, this is that same formula, just solve T. As you can see, the T and the V are around. So you then include this formula in with that old formula,